Today I'm going to talk about how to tell which scheduling policies have optimal response time tail decay. I'm Zeev Scully, a PhD student at CMU, and this is joint work with Lucas van Creveld, Onno Boxma, Jan-Pieter Dorsman, and Adam Weerman. Today's talk's all about the MG1 queue, a classic single server queuing model. So let's start by talking about what that is. We've got a single server, which can serve one job at a time, and a queue, which can hold any number of jobs waiting for service. This is what a job looks like. We're going to represent jobs as test tubes whose height is their size, or service requirement. And we're going to assume that we don't know any job's size. So these sizes are secret to the system. What we can do is we can serve each job. We're going to represent that as filling the test tube with water. And the progress we've made so far on a job is called its age. That is the amount of service it's received so far. The rest of the job is called the remaining size. So we can track how long we've served any job, so we know all the ages, but we don't know the sizes or remaining sizes. Now we have jobs randomly arriving over time. So at random times, jobs of random sizes arrive. And specifically, we've got a job size random variable, so all the job sizes are IID. We've got Poisson arrivals at rate lambda, and this gives us system load rho equals lambda times E of x. And this is the fraction of time in the long run that the server is busy, which had better be less than 1 for the system to be stable. So we're going to talk about scheduling today. So the scheduling policy is the algorithm that decides at every moment in time which job to serve. And it does so preemptively, so we can decide at any moment to switch from one job to another and start serving a different job. When we do this, we don't lose any work and there's no delay, so preemption is free in this model. Our focus today is on what's called response time of jobs. So a job's response time is the time from when it first enters the system to when it leaves, all done. Now, a job's response time is going to depend on its size, that is how much service it needs, but it will also depend on how long it has to wait in the queue, which will be determined in part by the scheduling policy. So our goal today is going to be to design scheduling policies to minimize two different response time metrics. The first is mean response time, that is the average response time taken over all jobs. The second metric is tail of response time, that is the probability of a job having a particularly large response time. Now, minimizing mean response time has been the subject of lots of work. Talking about the tail of response time, it's much harder to study. And so to make it analytically tractable, we're going to look at the t to infinity limit and try and get the best possible asymptotic tail decay. And specifically, we're going to do this in the setting of heavy tail job size. So this is, for example, a power law or Pareto distribution as the job size. So let's talk about what prior work exists. I'm going to make a chart with a whole bunch of scheduling policies, and for each I'm going to talk about how it does for mean response time and how it does for asymptotic tail of response time. So let's start with the simplest scheduling policy, first come, first serve. So first come, first serve just does the jobs in the order they arrive, and actually has really bad mean response time. This is because the mean response time depends on the variance of the job size, which can be really high. In terms of the tail of response time, it's actually the worst possible tail you can get, as long as you're not like idling while the system is busy or something very silly. And specifically what I mean by this is that the response time tail in the t to infinity limit is t times worse than the job size tail. So this is really bad. A policy that is better for the heavy tail setting is processor sharing, or PS. So PS equally shares the processor between all jobs currently in the system. It has okay mean response time, better than first come first serve at least, and it actually has the best possible tail decay. Specifically, the response time tail looks like the job size tail up to a constant factor. A policy that's even better in the heavy tail setting is foreground background, or FB. So FB always serves the job of least age. So FB has really good mean response time, better even than PS in the heavy tailed setting, and it also has that best possible tail decay. That is the same as the job size up to a constant. And I should say that both PS and FB, I said that they're the same as the job size up to a constant in terms of their tail decay. They also actually achieve the best possible constant. So we've got some policies with the best possible tail decay. What about the best possible mean response time? That honor goes to a policy called the Gittins policy. And now the way Gittins works is kind of complicated. It uses the job size distribution to come up with something called the Gittins rank of each job, and it prioritizes based on that. And what you need to know for now is that it has the best possible mean response time amongst all policies with unknown job sizes. Unfortunately, because Gittins is so complicated, no one knows what its tail decay looks like. So it's a hard problem to figure out what the tail decay of Gittins' response time looks like. So you might ask, maybe there's a simpler version of Gittins that we can study instead. So there is a simpler version of Gittins called SERP. This stands for monotonic shortest expected remaining processing time. And it was shown actually at Sigmetrics 2020 that SERP is a 5 approximation for mean response time. So it has really good mean response time, comparable to Gittins, and it's actually much simpler than Gittins. So this is looking good, but unfortunately it's still complicated enough that we don't know what its tail of response time looks like. So maybe there's something even simpler than SERP that we can analyze the tail of. So there is a policy called randomized multi-level feedback, RMLF. And RMLF is actually the best you can do for mean response time without using knowledge of the job size, even just the random variable, let alone the individual jobs' exact sizes. So if you don't even know what the distribution looks like, you can use RMLF to get the best possible competitive ratio for mean response time. And it's even simpler than SERP, which is in turn simpler than Gittins. But even though it's so simple, we still can't analyze its tail decay, or it still hasn't been done. So this is the situation we're in. We have a whole bunch of scheduling policies, some with the best tail decay, some with the best mean response time, none with both as far as we know. So what we're going to ask in this talk is, can we optimize both the mean and tail of response time? Looking at our chart again, there's an obvious place to start. It's all of these question marks. If any one of these question marks were a best, then we'd have what we want, right? A policy with great mean response time and great tail decay. And that's exactly what we show in this talk. We actually show that all 3 of these policies have the best possible tail decay. Gittins under certain conditions, SERP and RMLF always, at least in the heavy-tailed job size setting. Moreover, we actually prove a more general result. We give a sufficient condition under which a scheduling policy has optimal response time tail. So applying this sufficient condition shows that Gittins, SERP, RMLF, and more are all asymptotically optimal for response time tail, at least in the t to infinity limit. So in the rest of this talk, I'm going to formally state our sufficient condition result and show how it applies to Gittins, SERP, and RMLF, and then I'm going to give a high-level overview of our proof. So let's start by formally stating actually an easy version of the results. For the full statement, which is a bit too complicated to go over now, you can see our paper. So we're looking for a sufficient condition for a policy to have optimal response time tail. And the first question we should ask is, what are we even looking for? What does the sufficient condition, what might it look like? So the number 1 rule of scheduling is, don't let small jobs get stuck behind large jobs. And so we'd like our sufficient condition to basically say this, but in a more formal way. And this is tricky because there are a lot of scheduling policies out there that have a really wide range of behaviors. How do we formalize this idea of not letting small jobs getting stuck behind large jobs? And our first idea is kind of to narrow our focus a bit. We're going to narrow from all scheduling policies to a class of policies called SERP policies. So SERP policies pick which job to serve in a particular way, using what's called a rank function. We use a rank function to map each job's age, that is, service attained so far, to a priority called its rank. So a rank is just a number, where lower rank means better priority. So as an example, FB is the policy that always serves the job of least age. So under FB, a job's rank should get worse and worse as its age increases. So that's represented by this rank function, R of A equals A. all SOAP policies really work the same way at the end of the day, in that they always serve the job of minimum rank. Breaking ties first come, first serve. But within this one rule, just by varying what that rank function is, we can get a really wide range of policies and of performance. So we already saw FB. First come, first serve is also a SOAP policy. Namely, we can use our tie-breaking rule, just always give all the jobs the same rank, and we'll get first come, first serve. And we already saw that first come, first serve is as bad as possible for tail decay, whereas FB is as good as possible. So just within SOAP, we have this really wide range of policies and of tail performance. So it turns out that GITINs, MSERP, and RMLF are also SOAP policies. So this is a wide enough class to cover all the questions we had at the beginning. So for example, RMLF has the following rank function. It kind of looks like an exponentially rounded version of FB. And I'm simplifying a bit here because the R in RMLF stands for randomized, and I'm not showing the randomization, but this is the basic idea. RMLF kind of looks like first come, first serve, in that it's got these big flat regions in the rank function. But it also looks like FB in that the rank is going up over time. And so it's not clear a priori where RMLF should fall on the spectrum from worst tail to best tail. But what is clear is that wherever it does fall, it's going to depend only on what its rank function is, right? Because the only difference between first come, first serve, FB, RMLF, and every other SOAP policy is the rank function. So by focusing on SOAP policies, we get a key step, which is that our sufficient condition is going to be a condition on the rank function. So let's talk about what a sufficient condition on a rank function might look like. So let's suppose I'm using the SOAP policy with the following rank function, and I want to ask, do small jobs get stuck behind large jobs? Let's say I'm a small job. This is my size. My worst ever rank is this purple dotted line. So any job whose rank is above the purple line, I don't have to worry about, won't bother me. So the question is, can big jobs bother me? Well, yes, for this rank function, we can have big jobs in this age range that can have rank better than mine. And so big jobs can get in my way under this rank function. And so this sort of behavior in the rank function can lead to bad tail of response time. In contrast, let's look at a version of the rank function that isn't quite as wavy. So it's still got waves going up and down, but the waves aren't as extreme. Now I can look at my size, I can look at the same worst ever rank, and now because the waves are less extreme, none of the big jobs bother me. And so rank functions like this can avoid big jobs bothering small jobs and can have optimal response time tail. And so our sufficient condition is basically formalizing this intuition. So how do we guarantee that the waves of the rank function aren't too big? Well, one simple way is to ask that our rank function is bounded between, say, two curves, two polynomials. And so I like to think of this as a cone. So if our rank function is stuck inside a cone, and the cone is tight enough, that's saying it's not too wavy. And so for this cone to be tight enough, what that means is that our exponents on these bounds, gamma and delta, should be close together. So I'm now going to show you the full statement of the simplified version of our sufficient condition. And we'll see it basically formalizes exactly how close gamma and delta need to be to each other for tail optimality. So let's suppose we've got a MG1 with a heavy tail job size distribution, specifically intermediately regularly varying. And let's say we're scheduling using a SOAP policy whose rank function is stuck inside one of these cones, bounded between a to the gamma and a to the delta, where both gamma and delta are positive. So we've got this increasing cone. If the cone is tight enough, that is, if gamma and delta, their ratio is less than this quantity, which depends on the job size distribution, then the SOAP policy in question is tail optimal, that it has the best possible response time tail decay in the t to infinity limit. Namely, it matches up to a constant factor, that of the job size. And in particular, the constant factor we get, adding this 1 over 1 minus rho times x inside the probability, that turns out to be the best possible constant factor. You might be thinking, okay, this condition with the delta over gamma less than blah, 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 looks very complicated. Is there an easier thing to remember? And there is. It turns out that this blah, 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 blah on the right is always at least 1. So if you can get gamma equals delta, that suffices. So if we have a tight enough cone, namely if we have exactly the same exponents for gamma and delta, that will always work. So let's see how this condition applies to the policies we've seen so far. For FB, we can bound its rank function between two lines. So we get gamma equals delta equals 1, and we're happy. Has the best possible tail. First come, first serve. Because we're looking for positive exponents, there's no way to fit it inside a cone, because the bottom edge of the cone will always eventually get bigger than the constant rank of first come, first serve. So first come, first serve doesn't fit inside a cone, which makes sense because it's got the worst possible tail decay. RMLF, now we can see where it falls on the spectrum. It fits between two lines. It's got gamma equals delta equals 1, so it's got the best possible response time tail decay. Let's look at MSERP now. So MSERP has a more complicated rank function than RMLF that's based on the job size distribution, specifically expected remaining size at various ages. It looks something like this. And I don't have time to get into the details, but you can show that in the heavy-tailed case, when X is a heavy tail, this expected remaining size stuff is always theta of A. That is, our rank function is bounded between two lines. We've got gamma equals delta equals 1, MSERP is tail optimal. How about Gittins? Gittins is even more complicated than MSERP. And I'm not showing you the full formula for its rank function. What's important, again, we're just looking for bounds to show it fits inside a cone. It turns out Gittins has rank less than MSERP's and greater than something to do with the hazard rate of the job size. And so what this means is that we can get an upper bound on Gittins using the fact that MSERP is bounded. For the lower bound, we have to make an assumption on the hazard rate of the distribution. Specifically, we need to show that the hazard rate doesn't have really big spikes at really late ages, which we formalize as hazard rate being bounded as a to the negative gamma for some sufficiently large gamma. And in particular, gamma equals 1 will always suffice. Okay, those are our results. Let's talk very briefly about how we prove them. So here's a bird's eye view of our proof. We're trying to prove that various policies have optimal response time tail. There are several techniques that exist for doing this. We use one based on work of Núñez-Queja and a method he introduced in 2002 that bounds the response time tail using moments of size conditional response time. So Tx is the response time of a job of size x. So now the question becomes, how do we get these size conditional response time moments? For that, we turn to the SOAP analysis introduced at Sigmetrics 2018, which shows how to analyze the response time of any SOAP policy. And in particular, it bounds these response time moments in terms of moments of busy periods in an MG1 queue. And these aren't the same busy periods as the original system. They're transformed in a way that specifically using the rank function. So this is where the rank function comes into play. So if we have small enough busy period moments, then we get small enough response time moments, which will give us tail optimality. It turns out to get the sharpest possible bound, we need to look not just at integer, but also at fractional moments. And for MG1 busy periods, that actually hadn't been done before. So we came up with a new bound on fractional moments of busy periods that's sharper than previous bounds. And we plug this into a new version of SOAP, which we then plug into a new version of Núñez-Queja's method to get tail optimality. So to summarize, today we talked about a sufficient condition under which a policy is tail optimal, has best possible response time tail decay. And it rests on two key ideas. The first is that we stated our sufficient condition in terms of the rank function of a SOAP policy. And the second was that there are several key technical steps that go into this, one of which is bounding fractional moments of MG1 busy periods, a result that can be of independent interest across queuing theory. So I'd like to thank you for listening to this talk. If you have any questions, please get in touch. I'd love to hear from you at zscully@cs.cmu.edu. Thanks again for listening.